In this unit, we start looking at perhaps the most important problem that information theory has more or less solved, the channel coding problem. And we will start by describing the problem first and present a naive scheme. So in this problem, the goal is to send a message over a noisy channel. So a message for us is a random variable or an unknown m, which takes values between 1 to, let's say, capital M. And this is something that you send, and you send it over a channel, and you are allowed to modify this message the way you want so that it can be sent over the channel. So you encode the message, and then you get some sequence of inputs for the channel, let's say x1 xn, and this sequence is sent one by one over the channel w, and you receive something at the output y1 y2 yn, and then you again do something, you decode to get the final output m hat. And let me make it a capital M to let me make it u hat. So the goal is that this u hat matches your message m with large probability. Okay, that's the goal. And this channel, just to quickly remind you, it's been a while since we saw a channel. Channel W has an input alphabet and an output alphabet. Input alphabet, output alphabet. And here we are not using the channel once, we are using this channel n times. And in each time, when we send xt at time t, okay, I'll just write it here. When we send xt as input, we get, I should make these guys capital because these are random variable, whereas these inputs can be deterministic functions, can be just a function of m, so they can be fixed. We get yt, which is distributed as w given xt. Okay. That's the channel thing. So every time you use this channel for transmission, and you get to use the channel multiple times. And we want to ensure that the average probability of error is small. We want to ensure small average probability of error. So that is, you want that this average probability that you had the final output decoded message is not equal to m, given that m was sent. This average probability of error is smaller than epsilon. So this epsilon here is the acceptable probability of error that you have. Okay. And the question that we want to answer is, how many messages m, maybe how many bits of messages, so that's log n, how many bits of messages, how many bits of messages log m can be sent per channel use. Okay, so per channel use. So channel is like a resource. So for example, you can think of a communication system where such as Wi-Fi, where each transmission will have some delay and it will consume some radio resources, and you have to ensure that you send as many messages as possible per channel use. Okay, per transmission. Okay, so that's the problem we are after. So before we proceed, let me say that throughout we will restrict to we will restrict to so-called memoryless channels. We have already seen this phrase before, so I'll just quickly revise it. So what does it mean to say the channel is memoryless? Which means that when we send n symbols, each transmission sees independent noise. So you send n symbols and you see y. What's the probability of seeing y1 to yn at the output, given that the input is x1 to xn? This probability will split into independent parts. This is the memoryless assumption. It's w of yt given xt. Okay. Also, the channel remains the same. Doesn't matter where we are. It's just to make the same. Okay. So this is what we call n uses of the channel. Okay. So just to take some specific examples. The following three channels have received a lot of attention. For the communication problems. So they are important for practice. So first one is the so-called binary symmetric channel. So that's the first channel that has received a lot of attention, and this is abbreviated as BSC and with a parameter delta. So what this channel does, its input alphabet X and output alphabet Y are both binary. So it just sends bits and receives bits. But when you send a 0 in this channel, you can receive 0 with some probability 1 minus delta, but you can flip it with some probability delta. And similarly for 1, you can receive 1 correctly with probability 1 minus delta, and you can flip it with probability delta. So it's symmetric because the probability of flipping 1 to 0 is the same as probability of flipping 0 to 1. Okay. So another view of this channel is y equals to x plus z, XOR of z, where the z is Bernoulli half. So you just add Bernoulli delta. You just add a random noise to it. So when the z is 1, the bit flips. So that's why it's Bernoulli delta. This is the binary symmetric channel. It's a very nice abstraction for a very complicated communication system. You can just imagine that system as transmitting bits, which it flips with some probability. Okay. The next channel is the next important channel that has received attention is something called the binary erasure channel. which again sends bits, but instead of flipping the bits, it can result in erasure of bits. So you get to know that there is some problem with the bit and it has been erased. And this is a good abstraction for things like networks, where there are protocols implemented to first check if what you have received is correct or not. So this one has input alphabet X, which is binary. Output alphabet is no longer binary. It has a special symbol, maybe bot, which denotes erasure. Okay, so this special symbol here denotes erasure. Okay. So this again, this guy we abbreviated as BEC and associate a parameter delta with it. So you have this 2 input 0 1 with probability 1 minus delta, you receive it correctly. Probability 1 minus delta, you receive 1 correctly. And what happens with probability delta is that this guy gets erased. And this symbol signifies that you get to know when there is a problem. So when you see a 0, you know it must have been the 0. When you see a 1, you know the transmission must have been 1. But when you see a bot, then you don't know what the transmission was, but what you know is that some error has occurred. Okay, that's what a binary erasure channel does. Okay. The third channel that is very important from communication point of view is the additive Gaussian noise channel. And this one has X and Y both as real numbers, and the channel transition is defined by a density now, which is given by 1 by root 2 pi exponential of x minus y square by, say, 2 sigma square. Let me just put sigma square. Okay. So one can view it as the output y being x plus z, where z is a Gaussian with mean 0 and variance sigma square. So you add this noise to the input. That's why it's called additive Gaussian noise channel. Okay. This channel has both input and output continuous. Okay. So in information theory, and especially for when we are looking at application to communication, we really want to understand how we can send messages reliably over these channels, and they're all noisy channels. Okay. So the first thing that we can try to think about is some naive schemes for transmission over BEC/BSC. And this naive scheme is what is called the repetition code. So what this code does, it just repeats the transmission. It just keeps on sending the same thing again and again until it thinks it's correctly received. Remember that for any message M, I can encode this by a given sequence, and any message here I can encode it by a given sequence. And the encoding that we do here is by just repeating the message. Okay, so let's try to analyze this scheme now. So the basic scheme that we have is very simple to describe, the repetition code. Let's start with looking at a BEC, the binary erasure channel. Okay. So what we do is, given a bit M, send x1 equals to x2 equals to xn equals to m. Okay. We just send it, repeat it. Then When will this transmission be successful? Then probability of no error equals to probability that, or probability of error equals to probability that all x1 to xn get erased. And this probability, this particular probability is, each erasure happens with probability delta. This is delta to the power n, right? And we want this guy to be less than equal to epsilon. Therefore, we must choose n to be greater than log 1 by delta by log 1 by epsilon. Okay. So we can send, that's the number of transmission you need to send, 1 bit. So the number of messages sent per channel use is 1 by this guy, log 1 by epsilon this is a small mistake. So we want n to be greater than log 1 by epsilon by log 1 by delta. Therefore, we can send log 1 by delta by log 1 by epsilon bits of messages per channel use over a BEC using the scheme, the repetition code scheme. The decoding scheme for repetition code is very simple. If you get even one of the x1s unerased, you know exactly what the input is. So the only way you'll have error is if all of them are erased. Okay. Let's do a similar analysis for the BSC now. In the BSC, the repetition scheme can be defined the same way. We just repeat the thing. But we have to, so encoder is still the same. Encoder E of m is equal to x1 to xn. This is a sequence in xn where all xi are equal to m. But the encoding is very simple. And here again, this m is a bit that you want to send. The decoder now requires some thought. So to design the decoder, let's see what is the distribution of the output given the input. For a bit m which is sent, when it's sent n times, what is the probability distribution of the output sequence yn belonging to 0? So let's just yn belonging to 0, 1 to the power n has the following distribution. The number of times you see m here, all those instances can happen with probability 1 minus delta. And the number of times you see 1 minus m here, all those instances can happen with probability delta. So delta to the power, let's look at the number of times this yi equals to the distribution of probability that yn equals to yn given that E of m is sent. Okay. The input of the channel is E of m is equal to 1 minus delta to the power number of times this yi is exactly equal to m, because that's the times in which no error occurs, and delta, this is the time, this is the instances where error occurs, delta to the power I equal to 1 to m, indicate a function that yi is not equal to m. Okay, you can verify this thing. Therefore, so this is the distribution of this guy given m. Therefore, the maximum likelihood rule, remember this maximum likelihood estimate or decoder rule is given by maximum likelihood is the one which will choose that value of m which maximizes this probability. So you will declare 1 if the probability of this guy under 1 exceeds the probability of this guy under 0. So it says declare 1, let's put it this way, it's the probability of, look at the probability of y given that the input m, let's denote this input bit by b. If this probability exceeds the probability that the output is y given that the input is 0, then you declare 0. That's just a compact notation. So what does it mean? So which is the same as, now you can write it, 1 minus delta to the power number of times you see 1, delta to the power number of times you see 0 is greater than 1 minus delta to the power number under 0, this is n minus k and this is k. And you can simplify this further, and what you will get is k log 1 minus delta by delta is greater than equal to n minus k log 1 minus delta by delta. Okay. So if delta is less than half, then this guy is positive, then the ML rule, maximum likelihood rule, is given by, you declare, so here in this I'm denoting k as the number of ones in ym. So then the ML rule is given by, you declare, you compare k with number of ones with number of zeros, and if this number of 1 exceeds number of zeros, you declare 1, otherwise you declare 0. So same as the majority rule. Okay, majority decoder. Look at the output sequence. If it has more ones, then you declare 1. If it has more zero, then you declare 0. If both are equal, you just take a random guess. So now let's look at the probability of error for the majority rule. So probability of error. So an error can happen only if the number of flips, for the majority rule, you can check this, the number of flips, the number of times zt, this zt is the random variable which zt equal to 1 means there's an error at time t. If this number of flips exceeds half, so if error happens, number of flips must exceed half, otherwise no error will happen. Right? If you don't flip more than half the time, then no error will happen for the repetition code. So it must exceed half, and this probability is less than you can divide by n vt zt minus delta is greater than equal to half minus delta. Okay. So what is the probability that this is greater than equal to half minus delta? So this random variable zt, remember z1 to z, these are the error, these are the noise in our, I told you when I was describing binary symmetric channel that you can model it in this form. So these are these z1 to zt. These are all IID Bernoulli delta, and they're IID because channel, they're independent because channel is memoryless. So they are IID Bernoulli delta. So what's the probability that the sample mean exceeds delta? Well, this is something that we have seen. You can do it this by Chebyshev, but the real estimate that you can get, you can actually show that this is, I'm not showing this proof, but you can show that this is exponentially decaying in delta, and this inequality has a name. This is the Hovding's inequality. So this bound is using an inequality which I never covered. It's called the Hovding's inequality. It's a strengthening of things we have seen earlier, like Chebyshev's inequality, and this gives an exponential dependence. Okay, you can show this. So this holds, and Therefore, if we want this error to be less than epsilon, so what we have is, therefore error is less than epsilon if this guy is less than epsilon. That can only happen if n is greater than log 1 by epsilon by 2 into half minus delta square. So this implies we can send the reciprocal of this 2 into half minus delta square by log 1 by epsilon bits per channel use. So that's what we get. Okay. This, by the way, this should be not log, but it should be log to the base e. So I'll use log here because log we have reserved for log to the base 2. Similarly here, I think in the previous one, here it doesn't matter actually. Oh, sorry, not here. Here, yeah, it doesn't matter. It's the ratio here. Okay. Okay, so this guy here, it was log 1 by delta, and here it is 2 into half minus delta square. So one thing we can compare is that we can check how this guy compare with ln 1 by delta, which is bigger. So as delta goes to 1, as delta goes to half, this guy goes to 0, and yeah, so you can compare these two and see which one gives a better performance. Okay, but these were just upper bounds. Okay, but the important point is, should we be happy with this result? Okay, so here is what we want. These are the number of bits we can send per channel use. So now note that if we want vanishing error, very small error, which is basically epsilon going to 0, then both schemes can send. So if you take limit epsilon going to 0 here, this guy goes to infinity, so this becomes 0. Similarly, if you take epsilon going to 0 here, this guy becomes infinity, so the overall thing becomes 0. So not both schemes. Repetition code can send asymptotically as error becomes 0. 0 bits per channel use. For both BEC and BSC. So the question is there a better code? Is there a better code that can send positive number of bits per channel use? As epsilon goes to 0, as error vanishes. Okay, so this is the question we want to answer. Is there a code which can do better than this? And one of the fundamental results of information theory is yes, there is a code which can have a positive rate, and in fact which can send positive number of bits per channel use. In fact, we can exactly characterize the maximum number of bits that can be sent per channel use for vanishing error or even for a fixed error. And that's what we will discuss in the next lecture. Okay, see you in the next class.